As LLMs grow, they face a scalability crisis. Dense models require every parameter to fire for every token. Today, we explore the architecture that breaks this limit, mixture of experts. In a dense model, the computational cost scales directly with the parameter count. MOE models are sparse. They decouple the model size from the compute cost per token. The core idea is to replace standard feed-forward layers with a set of experts. While the self-attention mechanism remains shared, the processing of information becomes specialized. But how does the model know which expert to use? Enter the router, a gating function that determines which experts are most qualified to process each incoming token. Most MOE architectures use top K gating. For each token, the router selects only the top 1 or 2 experts, keeping the rest of the model's massive weights inactive. Over time, these experts specialize. One might become an expert in logic, another in creative prose, and another in specific programming languages, creating a modular brain. This allows for staggering scale. We can build models with trillions of parameters that still run with the inference speed of a much smaller model because only a fraction of the weights are used. Training also becomes more efficient. MOE allows for massive parallelization, as different experts can be trained on different parts of the data simultaneously across a distributed network. This is achieved through expert parallelism, a technique where experts are distributed across multiple hardware nodes, carefully balancing the load to maximize throughput. However, MOE introduces new challenges. If the router isn't balanced, a few popular experts can be overwhelmed while others are ignored, a problem known as expert collapse. To prevent this, an auxiliary loss is added during training, effectively penalizing the model if it doesn't utilize all its experts in a balanced way. The trade-off is communication overhead. Since tokens must be routed to specific GPUs, the speed of the interconnect between your hardware becomes a critical bottleneck. While inference is fast, the memory requirement is still massive. To run an MOE model locally, you still need enough VRAM to store every expert in the mixture. Models like Mixtral and the speculated architecture of GPT-4 have brought MOE into the mainstream, proving its effectiveness for high-performance production AI. The beauty of MOE is its dynamism. The model effectively reconfigures itself for every token, ensuring the right expertise is always at the center of the computation. This modularity also points toward a more sustainable future, where specialized components can be updated or improved without retraining the entire monolithic model. The future of sequence modeling is increasingly sparse. Researchers are developing even more flexible routing methods to push the boundaries of digital intelligence. In summary, Mixture of Experts uses a selective routing mechanism to activate only the most relevant parts of a massive model, maximizing both quality and efficiency. For the developer building production systems, mastering MOE is essential for deploying state-of-the-art reasoning on real-world infrastructure. MOE reminds us that the path to true intelligence isn't just about size, it's about the precision and modularity of how that size is used. Our technical series is just getting started. Join us in the next episode as we explore the world of reinforcement learning from human feedback. Follow along for the journey.